right, so far we have studied the goodness of fit test, but I told you in the beginning that there were three tests: goodness of fit, association and dependence, and homogeneity. Now, goodness of fit test is a good one to use if you have categories like blue, green, yellow, whatever, and then you have values. These two tests are what happens when we have two uh, variables. So if I have blue, green, and then I want to see if male or female has something going on, and then I can fill in my values here. So this would make a kind of a matrix situation when you're dealing with two categorical variables, where goodness of fit only has one. Now we'll explain these a little bit more in depth. Now, for homogeneity and independence, they're very, very, very similar. Uh, we're going to collect SRSs from the populations, and we're going to just try to classify them. We're going to try to find the chi-squared statistic and get an x squared that approximates your chi-squared. But the degree of freedom is the rows minus 1 times the columns minus 1. So if I have a matrix, say blue, green, yellow, and dogs, cats, and fish, and I'm filling in these values: 8, 4, 2, 3, 2, 1, 7, 9, 11. So if these are our values, our rows are 3. So 3 rows, we have 3 columns. So row minus 1, 2, times column minus 1, which is 2, gives us a degree of freedom of 4. All right. Now our expected count is different here as well. We take the row total times the column total all over what I like to call is our total, n. So if I go back to this previous slide, if I want to find my expected count for this first spot, what I do is I take my row total, which is 14, or my column total, my row total, which is 18, and I divide it by our total, which is the number down here. Which is a total of 47. So if I want to find my expected counts, my expected values, the first value in the upper left-hand corner would be 14 times 18, all divided by my total, which is 47. Now my next value here would be 6 times 18, all divided by the total of 47. This column here would give us 27 times 18, all divided by 47. The next row, 13, 15, I would start with 15 times 14, all divided by 47, and so on until I get these two, and then this value, and this value. And those are our expected counts. Now, we can safely use chi-squared if, for the chi-squared distribution, when no more than 20% of the counts are less than 5, and all expected counts are greater than 1. In a 2 by 2 matrix, the tables should all be 5 or greater. So typically, all the values will be greater than 5, and so from that makes our condition. Also, we have to make sure that the data comes from an SRS, like always, and then check that all points are greater, all expected counts are greater than 5. If one value or a couple values are greater than 5, you got to check to make sure no more than 20% are less than 5. Now, a chi-squared test is for comparing two proportions. We can either use a chi-squared test or a z-test. A z-test gives us more flexibility in choosing greater than, less than. A chi-squared test is always a two-sided test. Now, there's one major difference between the tests of independence and homogeneity, and it's how the data is collected. In chi-square tests for independence, data come from one SRS. So all the data comes from one SRS, and then you take each data point and you put it into your 2 by 2 matrix. In homogeneity, data come from multiple SRSs. So for instance, if uh, I was going to do a study and I wanted to see how the school broke down on gender, I could take one SRS of females, one SRS of males, and if I did that and put them in a table, that would be homogeneity. But if I took one SRS of the whole school and threw that in a table, it would be a test for independence. All right, we're